Go from current slide. Now, before we hit into that, though, let me go over these announcements again. Okay. I think I announced these last week, and I asked if any of you are graduating this term, and none of you were, I don't think. Okay. Any in the spring? No. If you know of anyone who's graduating in the spring, this is the ideal time to start the applying for graduation. It's a three-step process. You first do a degree audit, basically come up with your degree plan. Then you see your advisor. Great time to do that with that degree plan in hand. And then once we get the spring schedule up, then you can go on and register for spring classes. If you determine that there's some courses you need that you won't be able to take in the spring, you might still be able to talk to that department chair, instructor, whoever, see if they can add the class, because sometimes we'll do that, okay, especially if someone needs it to graduate. If not, then check and see if we can do a course substitution. And that takes a while, so that's a good thing to get started now rather than waiting until spring term, because then it's going to be too late to register for it. So please start that process now. And remember, when you're ready to graduate, apply the term before you think you're going to be graduating. Always do it the term before. That allows yourself the flexibility of getting everything done when you need it. Okay, I think I announced to you before they're looking for note takers and they're looking for tutors. Math tutors, y'all would be the prime candidates for that. But also English, biology, computer science, and Spanish. So if anyone can do any of those, they pay you for the note taking, they pay you for the tutoring, and it's just a good deal all the way around. Okay. Mark the roll. Any questions on, one other announcement. I don't know if you noticed, I'm dressed a little differently today, and the reason is there's a good friend of ours' father died over the weekend, so I'm going to the funeral this afternoon. So I will not be on campus from 2 to 6 like I normally am. I'll be here probably a little after 2 as I'm getting things together. And if I do come back to campus, I'll go back to the Birmingham campus. I don't know how long the funeral and the other things are going to take. I'll go back to Birmingham campus rather than coming back here because it's such a long drive to get here, and it's much I can get there quicker. Usually. Sometimes not, but usually. Okay. All right. Any questions or anything we covered so far? Or any questions in general? Okay, we're in Chapter 5, which is logarithmic, exponential, and other transcendental functions. 5.2 is natural logarithm function integration, and we had done example 1, and then they didn't have example 2. Let me just make sure I'm saying this right. Yeah, they don't have example 2 or 3, but we've already done those, and we're ready to do example 4. Any questions before we get started on this? Okay. Example 4. There's several possibilities here. Here's the first. 3x squared plus 1 over x cubed plus x dx. Okay? What would be your approach to trying to find the integral?
Look at the most difficult problem.
Say again?
Look at the most complex problem and then.
Okay. What is the most complex part of that problem?
Problem says 3x squared plus 1. Is that correct?
Okay. Actually, here's the things I usually go by complexity. The highest exponents and being in the denominator. And one thing solves both of those. What is it?
X cubed.
Okay, what will you do with that once you decided that was going to be your most complicated part? Yeah, XU plus X, that's what we determined. What do you do with it? Why did you pick it out anyway? Why did you want the most complex part? What were you going to do with it once you had it?
Set it equal to U.
Yeah, that'd be your substitution thing. Is that what you said? Okay, I couldn't hear. Okay, sorry. So let U equal that complex thing, X cubed plus X. Then what's always your next step? Then du is equal to what? 3x squared plus 1. Ding, ding, ding. Look at that. That's your numerator. Say again?
So we have a dx at the end of that?
Yeah, dx. You're right. That's now your numerator. 3x squared dx. Exactly. I was so excited to see that. That's off my dx. Okay. All right. So what do we have now? The integral of du over u. Okay. And what does that become? Oh, that's been a long weekend. Yes. That's the integral of du over u.
3x squared.
Second?
3x.
Okay. And don't get the x's back in there. What's the integral of du over u? Maybe look at theorem 5.5 on the previous page if you got your book. Oh, maybe you don't have your book. Okay. What is that? If it would help to write it this way, integral of 1 over u du. Would that make it any better?
So it's the absolute value?
What about the absolute value?
U?
Well, that's in there, but what's the first part?
The log of the...
Yes, the ln log of absolute value u. With one other little thing, plus c. Okay? Now we go back and plug in what the u is in terms of x, and that would be now the log of absolute value what? What was our u?
X squared.
X cubed plus x. Absolute value plus c. That's it. Okay? Do you see where that comes from? Here's where we started. Now, most complicated part of this is almost always the denominator. Maybe not always, but most of the time it is, especially since that's higher exponent. Because if you let that be your u, and then take a derivative, you're going to get a lower exponent. And lo and behold, you get exactly the numerator times dx. So that then means that your integral becomes this thing here is your du, or you could have just put 1 over u du, okay? Or just du over u. Either one of those is log u, okay? That is the definition of a log. It's the integral of 1 over x dx, 1 over u du, 1 over a dA, whatever, you know. And then once you get that part done, plus your c, you go back and plug in what your u is, which is x cubed plus x. Now, if that had been, it's not, but if it had been, say 3x squared plus 1 here, then you could lose the absolute value sign. Why?
Because it'll always be.
That is always positive. X squared is always positive. 3 times x squared is always positive. Add 1 to it is always positive. So yeah, but on this one, because that could come up being a negative number, you have to use the absolute value. Okay? And the absolute value bars, when it's always positive, is okay. It's just not necessary. All right. Does that make sense? All right. Let's do the B part. Can I erase this?
Yes, sir.
Okay. Okay, the B part. The integral of sine squared x over tangent x dx. That's secant squared x. Secant squared x over tangent x dx. Okay. Now there's at least 2 ways you can approach this problem. How would you want to approach it? Say again?
The denominator,
The what?
tangent x.
I can't hear.
Let u equal tangent x.
Yes, that's one very simple, straightforward way to do it. Let u equal tangent x. Now, I admit sine squared, secant squared looks more complicated than tangent x, but tangent x is living in the denominator, and that trumps here. Oh, I don't want, never mind. Okay, let u equal tangent x. Then what's our next statement? Then du is equal to, anyone remember what derivative of tangent is?
Is it, I was going to take a guess and say secant squared.
Oh, you guessed well. Okay, and if you go to the very front inside cover of your book, you see your sine functions there. Number 15 is d by dx of tangent x is secant squared, or tangent u is secant squared u. You got it. Okay, so that would be secant squared x dx. All right, and what does your integral become now?
Say the log of absolute value.
Okay, yeah, he jumped right into it. Du over u, which then would evaluate to be the ln of u, absolute value of u, plus c, which would be the ln of absolute value tangent x plus c. Now, tangent x, remember, can be negative or positive, so that's why we have to have the absolute value bars there. And for an indefinite integral like this, I guess that's okay. All right. If that were a definite integral, you do have a couple things you need to worry about. And here's what they are. Tangent x is not defined at pi halves, or any half pi. Any half pi. So if your limits of integration went over across the half pi, you have to throw it out. It will not work because you cannot integrate discontinuous function. Okay, so but with an indefinite integral, yeah, you can just leave it like that. Do it. Goodness, my throat's.
Can
Yeah.
we go over what exactly integration tells you?
What's that again?
Like, what does integration tell you? Like, what do you?
Okay. Remember our good old Riemann sums? That's what it's telling you. It's summing let's do the du over u. 1 over u looks something like this, right? And then like this. That's the function 1 over x dx, 1 over x. And if you're integrating that, you're taking the area under that curve, or this one would be a negative over here. But that's what it would be telling you, the area under the curve between whatever limits you are. Now with an indefinite integral, it's hard to see what it is. It's just an antiderivative, and that's what you did with an antiderivative. But what an integral tells you if you have limits is between here and here. What's the area under that curve? Does that answer what you were asking? Indefinite integral is just antiderivative. What's the antiderivative of 1 over u is log u. Absolute value.
That's what I was trying to picture was how does secant squared x over tangent x?
Yeah. Well, that's why I went to that one. It's easier to picture. Then what you would have were the limits. The output of a tangent x, that's what you're taking the log of. So that would be, your x, you're taking on values. Hey,
Doc, sorry to interrupt.
Yeah.
Just want to borrow some markers.
okay, I
We
know.
got more up the hall.
I know 2 of these are new ones, I think. So I brought them in case you needed.
Appreciate it.
I don't know if those are the 2. You might want to check them.
Yeah.
Okay.
I hope these work.
Okay.
Appreciate it. Sorry to
All right.
interrupt.
No problem. Okay. Thought we had another student who was stuck with Brian, and then we lost a student, but okay. We're all back okay. Then these would just be identifying for values of x, which would be in radians, would be evaluating taking the tangent of those x values. That's what your input is on that curve. Yeah. So it is a convoluted way of looking at it, but that's what it is. Now I did say there were 2 ways to do this. Okay. Here would be the other way. Change this to sines and cosines. Integral of 1 over cosine squared x times cosine x over tangent x, over sine x. Because tangent is sine over cosine, since it's the denominator, it would be that. So that would be this, and that would be a pain in the neck to do. So you did well by choosing that method. I thought that might come out something pretty neat and handy. It doesn't. Okay. So, but sometimes there's another possibility. Okay. So let me go on and here's that's right. So we're just missing Daniel and Jordan. Okay. So let me erase this. We're doing example 4 near the bottom of page 325 in section 5.2. We just done the A and the B parts, so let's do the C part. The integral of x plus 1 over x squared plus 2x. And then we'll have a dx after it. Okay, what would you suggest that we do first? Example 4C, page 325, section 5.2. Any ideas? None whatsoever.
Let u equal x squared plus 2x.
Ah, good choice. Let u equal x squared plus 2x. Oh, here's Jordan. Let's see, Jordan's here. If Daniel were to come in, we'd have perfect attendance again. Let's hope he makes it. Then what would be your next step? Du is equal to 2x plus what? 2
Plus d, no, plus d, but d.
times du. dx. dx. You did the du on the other side. All right. What seems to be a problem here, Houston?
It's not natural.
That's not the numerator in the other, but is it anywhere similar? How so?
You divide both sides by 2.
Yes, if you divide both sides, so what you could do is factor out a 2. That'd be a x plus 1 dx, and then divide both sides by 2, and that wipes out, and then you have what you have in the numerator. So that would then be 1/2, that's the over 2 here, and that would be du, the x plus 1 dx, over u. And what would that be? Anybody? Okay, don't forget your 1/2. The ln of, yeah.
Absolute value.
Absolute value of u, okay, plus c. Okay, so now we can plug in 1/2 the log, natural log of absolute value of x. There's more, I just start at the first part. What's your u? X squared plus 2x plus c. Okay? Now there is one more thing you can do to that. And what would that be? A rule for logarithms. Okay. That is the log of x squared plus 2x to the 1/2 power. Yeah. Okay. Plus c. Now that leads to an interesting point. Do you still need the absolute value bars? That's what I was going to ask. Because see, this then you can write as the square root of this. And the square root of this is always a positive number. As long as what's inside there is not negative. So there's a sense you sort of still do need it, not for the logarithm anymore, but for the square root. You need that to be a positive number. And they do leave the, well, they didn't even take it the next step. Sorry about that. They left it in the previous step. Okay, which is perfectly fine. I just took it one more, and I thought that might relieve the need for the absolute bars, but I think you still need them. All right. Any questions on that? Okay. All right, to erase. All right, let's do D. For example 4D, the integral of 1 over 3x plus 2 dx. Okay? What would you do in a problem like that? And again, there's one of two ways you can, at least two ways, excuse me, you can approach that.
The substitution, but what's the other way?
Say again?
I said, we know the substitution, but what's the other way?
Okay, well, let's do substitution then. Okay? What would you do?
Make u equal 3x plus 2.
U equal 3x plus 2. Way to go. Okay? Then, du is equal to
x. I just want to say x, because when we take the derivative of 3x, this leaves x.
you're taking derivative of this thing.
Right.
What would that be? 3
Okay.
and but you're doing a differential of it, so that'd be 3 dx. 3 dx, right? Up here you only have a 1 dx, so what would we do? Divide both sides by 3. What's that? You could, but when that denominator is to the minus 1 power, then you know that's going to integrate as a logarithm. Any other power, a fractional power, any power greater, even less, stuff, but if that power is 1, you want it to be 1 over x, 1 over u du. That's what you can integrate. Anything else, yes. But now if you recognize that the integral of u to the minus 1 du is log u, yeah, then that's fine. But most people will recognize that closer like this, 1 over x dx, 1 over u du. So what do we have then? What does that integral become? 1/3 the integral of u over du. Du over u. That's what I thought you said. Okay, du over u, right? And that would be 1/3 log of
absolute value of u.
right. Something else plus c. Okay, and then what's that? Okay. The reason you have to put absolute value there, you cannot ever take the log of a negative number. So therefore, you have to put absolute value there. Now, if that term came out being always positive, this one doesn't, you could then lose the absolute value bars. But this one does not. That could be negative. Say for x equals -2, that would, or even x equals -1, that would be a negative number. So the absolute value bars require that to be a non-negative number. Now, what it doesn't require is also it can't be 0. And if x was equal to 2/3, that would give you no negative 2/3. Yeah, negative 2/3. That would give you 0, and you can't be that either. But you just know that it can't be that. But
It's because it's an area. You can't have a negative area.
well, no. Logs, you just can't take the log of a negative number. Like you can't take the square root of a negative number. You can't take the log of a negative number, but you can't even take the log of 0. So square roots, you can't take the square root of 0, but you can't take the square root of a negative number. Logs, you can't take the square root of 0 or a negative number. So you just have to eliminate those, and that's why you have to put in the absolute value bars. It doesn't eliminate the 0, but it does eliminate the negatives. But then let's go back and finish the problem. That would be 1/3 log of
absolute value 3x plus 2
plus c. And if you wanted to, you could then write this as the log of absolute value 3x plus 2 to the 1/3 power. Now, this is sort of interesting here. Because there is no requirement that this be negative for the cube root. It was for a square root, but not for a cube root. That would be fine. But a cube root of a negative number is negative. So you still have to leave the absolute value bars there. Because you can't have a negative number that you take a log of. So that'll be, now they left it in this form, they didn't take it to the next form. But either one of them are correct. And then they give these as possibilities. And they first put the 1/3 inside the parentheses, inside the absolute value bars. I don't know why they would have done that, but this is the way the second way. So those are all perfectly fine. Okay, that was example 4. Any questions? Y'all had some good questions. Glad, appreciate those questions. Now I think we're ready for example 5. So let's move on. We had already done 1. Okay. This is the verbiage at the top of page 326. Integrals to which the log rule can be applied often appear disguised in disguised form. Good. Okay. For instance, when a rational function has a numerator of degree greater than or equal to that of the denominator, the division may reveal a form which you can apply the log rule to. And that's what this example is going to be, which is a little bit different. All right. Find the indefinite integral of that. And I know, there is one technique that you definitely want to try. I was going to say there may be some others you could try, but this one you definitely need to try. And what do you think that would be?
Substitution.
Not yet.
Not yet. Okay.
Yeah, because you see that would give you a 2x if you use the denominator, and there's not a 2x in the numerator. So,
Factor
say again?
it. Factor it.
Okay, I'd like to see you. I can't factor either numerator or the denominator, okay? But you're welcome to try, okay? So yeah, that would be another good guess, another good thing to do. If they're factorable, by all means factor. These are not, okay? What would be another thing you might try?
Since we're just rounding up stuff.
Say again?
I said since we're just rounding up stuff, grouping.
No, you don't have an even number of terms in the numerator. You only have 2 in the denominator, so there's nothing really to group there. Okay. Now, again, think. The numerator is the same degree as the denominator. So, and it would also be even more obvious if the numerator were greater degree than the denominator. What could you do? Division, is that what you said? Yes, that's exactly what you do. Come off to the side here and do your long division of polynomials. What goes on the outside of the house? The bottom one, x squared plus 1 into, now let me back off a moment here. You don't have to do it here, but I think it usually works out better if you do. Okay? If you're used to it, you can get by without it. Never leave off a term. So it'd be x squared plus 0x plus 1. Because you see, you're missing a term there. You don't have to do that, not outside the house. Inside the house, you absolutely have to. But inside the house, you're okay. It's x squared plus x plus 1. So I didn't need that longer line. So how do we do our division? Flash to the past. X squared will go to x squared one time. Then you multiply. 1 times x squared is x squared. 1 times 0x is 0x, right? And 1 times 1 is 1. Okay. Okay. Now, here's why I was saying it's helpful to do this. You could have gotten by without that. Leave this off here, and when you multiply it, 1 times x squared would be x squared. If you didn't have that term there, you'd say 1 times 1. You would have to go over here and put it under the 1. You wouldn't put it under the x. So you just leave that blank if you didn't put that 0 term in there. But you would have to leave it blank. And then what do you do next? You subtract. And that subtracts to 0. Those subtract to 0. and this just gives you an x. Well, that's your remainder. You can't divide into it anymore, so your answer is plus x over x squared plus 1. Okay? Now, write down this expression here is what this becomes. That becomes this when you do your division. So that'd be the integral of 1 plus x over x squared plus 1 dx. Okay? Now, easier to split this into two integrals. The integral of dx plus the integral of x over x squared plus 1 dx. Okay? Hopefully we can all do this. What does that come out being? X. Okay? Now, the second one, what does it become? Now you do your substitution. Let what?
X squared plus 1.
Second?
X squared plus 1.
Yeah, but what about it? Let u equal x squared plus 1. Okay, then du is equal to 2x dx. Perfect. Now, up here in this problem, we don't have a 2x dx, we just have x dx. So what might we do? Divide both sides by 2. Okay? Now we have an x dx, so this part here, just this part here, becomes the integral, actually 1/2 the integral of, sorry, du over u, right? Which would then be 1/2 the log u, log absolute value u. Now, we can put the c here, we could wait till we put it back in there, but we only need 1 plus c. There's no reason to put 2 of them, one for this one for that one. So, but wherever you're going to put it, be sure you get it there. So the answer would be x plus, getting it back to x, help me. 1/2 log
absolute value x squared plus 1 plus c.
Okay. Except I didn't put absolute value bars. What's wrong with me?
Oh, because
Because it's always positive. Yes. X squared can't be negative. It could be 0. So that would be a problem. Except you have a plus 1 there. 0 plus 1. Can't be 0 and it can't be negative. So anything else you put in for x is going to be even more positive than that. So you really don't need the absolute value bars on that. And this one you could then write, if you wanted to, but it's not necessary, x plus the log of x squared plus 1 to the 1/2 power plus c. So that would be another way to write that answer. And they left the 1/2 out in front. Okay? So they left it in that first form. And then they say, check the result by differentiating to see if you do get the original integral, and I think you will. I haven't been showing those checking things because I was trying to speed through this a little bit. Is that okay? Do you see? Okay. Now, let's see how they do it. Let me clear all my chicken scratch off. Okay. Begin by doing log division. And notice they didn't put the plus 0 in here, which is okay outside the house. Inside the house, you absolutely would have to if you're missing a term. Outside the house, you don't, but then you have to be very careful here. X squared will go to x squared, and they put their 1 way over here, which is fine. Most lot of math books do that. I like it right there just as well. But 1 times x squared is x squared, and 1 times 1 is 1. But don't put the 1 here. Those are not like terms. Put it over here. Just leave it blank here. Okay? And that's fine. And then when you subtract, that goes to 0. That goes to 0. And this is just x. Okay? So this becomes 1 plus x over 1. X squared plus 1. And that's what you put back, excuse me, in the integral. God, gracious. My head's all clogged up, and I don't know why. And earlier this morning, goodness, my throat hurt so badly. I'm hoping I'm not coming down with something again. I did that last summer, and it was pretty miserable all summer long, but I hope it's not going to happen this year. Okay, rewrite the long division, result of the long division, and that's what that thing became. And that you can split into 2 integrals. One is dx, and the other is 1/2. Okay. All right. They did it a little bit differently. They put a 2x in the numerator, 1/2 of 2x over x squared plus 1, and that would be, obviously the 2's would go out and you get exactly that, but if you do it this way, then your numerator is your derivative of your denominator. So if you see that better, perfectly good way to do it. Okay? What they did from the previous step is just put a 2, take out this one, okay, that's already gone. And then on the second one, on the integral here, put a 1/2 on the outside of 2 here, and that would be your log du, basically. Okay. And that gives you x plus 1/2 the log of x squared plus 1 plus c. Now, they don't show the next step that you actually move the 1/2 over. But check this result by differentiating to obtain the original integral. Okay. That would be, differentiate that, you get 1, and this would be 1/2, 1 over x squared plus 1 times the derivative of 1/2, which is, I mean, 2x, which is x squared, which is 2x. 2's go out, and you're left exactly what you had. The derivative of c is 0, of course. So, yeah. All right. And by the way, that example 5 was also says see larsoncalculus.com. Sorry. For an in an interactive version of this type of example. Sorry about that. I don't know why this is happening. All right. Now, before we go to the guidelines, there is example 6. They're not showing in the slide set. So let's go back and do example 6. Any questions before we move on? All right. Find the indefinite integral of this one. The integral of 2x over x plus 1 squared dx. All right. Now, what would be your approach on that one? A little bit bizarre kind of a problem here. Later we'll learn there's another way you can do this, but we aren't there yet. So what would be your approach? Would you have an approach? Say again?
I thought about something. If you know, I was thinking about if you took people take the power, the square, that's in the denominator, and put it in front, and then you multiply it. No. I'm thinking.
I'm not sure I quite followed, but I don't think. Okay, would you say that one more time?
What I was thinking was if we took the square in the denominator and possibly get something similar to the numerator, but
Okay. Now,
still has.
I thought you said square root, but you said square. Okay. Now it's making a little more sense. Okay. If you square the denominator, that's exactly what I would have said would be a first possible approach. Okay. So let's try that. So that would be, if that's what you were saying, is it?
Square the denominator.
Okay, so that would be 2x is the numerator over, and what is the square of the denominator? Help me.
Be x squared
X squared plus what?
plus 2x
Plus 2x
plus 1.
plus 1. Now that was my first approach, but I'm not, okay.
Yeah, that wasn't what I was thinking.
Huh?
That wasn't what I was thinking.
Oh, that wasn't what you were thinking. Were you meaning square root? Okay,
But that we go that way.
okay. Well, what way were you meaning? See, that's why I wasn't quite following.
How long was it with rule? It's not the power rule, it's like another rule we used before that where we took the
Okay.
it's
In other words, say the denominator x plus 1 to the minus 2 power.
minus two kind of.
No, that wasn't it either. Okay.
That's not really many of those at least.
Yeah.
But yeah, let's
Well,
continue.
let's pursue this for a moment and see if it works. Okay? Because the good news is the derivative of this is going to be a 2x and there's a 2x. But the bad news is you also have a plus 2. Derivative of this also has a plus 2 that you don't have up there. Okay? So I don't know if it will work. But that was my first inclination, was to do that. Okay, well let's see what will happen. Let's try it. Let u equal x squared plus 2x plus 1. Then du is equal to, help me, 2x plus 2 dx. Okay, which would be 2 times x plus 1 dx, right? I'm not sure that's helpful to do that, but
Could you not just subtract 2 from each side?
you mean divide?
Well, we got the plus 2 right there.
Oh, you mean earlier, yeah. In other words, you say, right, this is 2x dx plus 2 dx. Is that what you mean?
No, I'm
No.
not saying like, it would be like du minus 2 equals 2x.
Yeah, but it's 2 dx. So you still, yeah. So far, that's not looking too good. But let's step back one more time. Not taking it the square here. I thought that might have possibility. It doesn't. Okay. Okay. But let's leave it in the form that he first did. And what was our original rule? Let the u be what? The innermost part of the most complicated part. What is the innermost part here?
X plus 1.
X plus 1. Okay? Then du is equal to dx. Okay? All right. But we still have a 2x up there. Well, here's something we can do with that. Let's take the 2 outside and have you just x over x plus 1 squared dx. That's legal, isn't it? Most states. Okay? So, Now we do that trick that we had a long time ago, back when we first started doing substitution, and let this represent, subtract 1 from both sides. This is where you do the subtracting. And you have u minus 1 is equal to x. Okay? So, this integral becomes 2 times the integral of u minus 1, that's your x, and your dx is your du, over u squared. Okay. Which would be 2, I'm going to split this into two integrals. U over u squared du minus 1 over u squared du. Okay, with the integral sign in front, and the 2 is outside all of it. Now, what does this give you? 1u disappears, right? And that gives you 2 times integral of 1 over u du. What was that?
It's going to be 1 over x plus 1 squared.
Say again? It's the integral of...
1 over the log.
Oh, that's the log. That's the ln of absolute value u minus... Now that I would write as the integral of u to the minus 2 du. That you wanted to do before, right? In this case, since it's not a 1 u to the minus 1, I would do that, okay? And what does that give you? Now the 2's out in front of all of it, log absolute value u, and what would that be? Antiderivative of u to the minus 2 du. We're doing an antiderivative. Okay? So that would be, will you raise that by 1, be u to the minus 1, right? Over a minus 1, which basically is going to change that sign. Okay? And then you have your plus c. So this would be 2 times the log of, and your u was x plus 1. Still need the absolute value sign, that could be negative, plus 1 over x plus 1 plus c. Now you could write that as 2 log absolute value x plus 1 plus 2 over x plus c. No, x plus 1, I'm jumping ahead of myself, plus c, which you could also then write that as log absolute value x plus 1 squared plus 2 over x plus 1 plus c. However you want to write that. Okay. Oh, man. My head is so completely jammed and I don't know why. Okay. Now, this one, I'm pretty sure you can now lose the absolute value parts, because you're squaring it anyway. So it doesn't matter if this is plus or minus. When you square that, you could. So in this case, I think it would be better to do that way and have your answer being log x plus 1 squared plus 2 over x plus 1 plus c. Now, a couple things to note. Obviously, x can't be negative 1. It can't be negative 1 here because you can't take the log of 0, and it can't be negative 1 there because you can't divide by 0. So in both cases, x can't be negative 1. So like that by the side or something like that. And they left it in there, in that, hey, where is that? I know I wrote it down somewhere. Right here. 2 log x plus 1 in absolute value plus 2 over x plus 1 plus c. Now again, in this case, I think to bring the 2 up would make a little bit easier. All right. They have a little paragraph at the top of the next page, which is a little interesting. Differentiation takes the form of here is the question, what is the answer, while integration is more like here is the answer, what's the question. In other words, you're doing an antiderivative. You're coming up with the question. So, based on those comments, that's why they go to this. The following are guidelines you can use for integration. Learn a basic list of integration formulas. Okay. Depending on how basic you are, if you learn them all, you don't even have to do them anymore. No, you wouldn't do that. Okay. But just get the basics down. Find an integration formula that resembles all or part of an integrand, and by trial and error, find a choice of u that would make the integrand conform to that formula. And that's sort of what we've been doing. When you cannot find the u substitution that works, try altering the integrand. You might use a trigonometric identity, multiplication or division by the same quantity, addition or subtraction of the same quantity, long division, be creative. Okay. Now, one of those back there, it was this one. There was another technique that we haven't done yet that you could have used, and we'll use that a little bit later. Okay. If you have access to computer software to find antiderivative symbolically, use it. I don't, but if you do, I guess you can. And then check the result differentiating to make sure you obtain the original integral. Okay, integrand. A lot of blah, blah, blah. Let's see if we can do example 7. Whoa! Here's a differential equation. We haven't done those, have we? We kind of did some, didn't we? Or did we? No, not at all. Okay. Here's what they do. Okay. Now this first step, you can say it one way and make mathematicians cringe, and it's doing the same thing, or the way they prefer to you say it, is write that derivative in differential form. So what would that be? dy is equal to 1 over x log x dx. That's writing that derivative in differential form. Y'all remember that, don't you? Sort of. Skim by it real quickly one time, maybe. The other way, if you want to think of it this way, is not good mathematical etiquette to do, but multiply both sides by dx, okay? That's not a fraction. It looks like a fraction, but it does the same thing. Multiply both sides by dx. Mathematicians cringe when you say that because that's an operator. It's not a fractional form, but it does the same thing. Okay? Now what do? You integrate both sides. Okay? Integral of dy is simply y. Okay? What do you reckon the integral of 1 over x log x? How are we going to do that? Okay. Yes, yes, yes. And what would be your substitution? Not quite. Just do the ln x part. The most complicated part of your, the innermost part of your most complicated part, whatever, and the innermost part is your log x. And why that? Then du is equal to, you sure should, because we've just been doing the antiderivative of it. Derivative of log is 1 over x dx. When we've been taking the integral of 1 over x dx, it always came out log, didn't it? That was the antiderivative, so the derivative is going the other way. If you have u equal log x, take the derivative, it becomes 1 over x dx. Now, if that's a little foreign, look at the top of page 324. Oh, you probably don't have your book with you. Okay. Go back to last week's thing, and we did that. D by dx of log x is 1 over x. And d by dx of log u is u prime over u. We did that quite a bit. I thought beat it to death. Okay. Now, with that in mind, what does this integral become? The 1 over x dx is, that's your du. So there's your du part. And then what do you have then? Well, 1 over u. Ooh, that's an ugly u, isn't it? Goodness gracious. Where did that come from? Okay. Okay. See the 1 over x dx, this part, 1 over x dx, that's your du, and then you have 1 over log x, log x is u, so 1 over u du. And then what's the integral of that? Help me. Antiderivative of 1 over u du. Always feel like we're running a circle, huh?
Isn't that
Log u, you got it exactly. So this is log absolute value of u. And you can do a plus c if you want to. Now we go back and plug in. And what is u? ln x. So it's the y is equal to the log of x. Okay? Now, this is really bizarre. You really need absolute values around both of them. Okay? All right. Plus c. All right. Now, why that? Well, obviously, no limits are given here, so x could be negative, so you need the absolute value around this. Then you're taking the log of this. If log of x is some small number, that becomes a negative number, okay? Or even if it's 1, it becomes something you can't take the log of, so you have to put that in absolute value bars too. And that's exactly what they do. Y is equal to log of absolute value log of x. Now they left the x inside, not in absolute values. And I'm trying to figure out why that would be the case.
So it's just ln and absolute value of ln x plus e?
What's that again?
I was trying to imagine it, so it's ln and then absolute value bars ln x plus c.
Yeah, that's what they said. They just left off the absolute value bars in here.
That's what I was going to ask you. If we didn't need those two bars right there, wouldn't the problem still be the same? Because the absolute values on the outside would take care of it and make sure it's not negative?
Yeah, but if x were negative, you can't even get to the outside because you got to take the log of that negative number. And I can't see any reason it can't be negative. Unless, of course, you say by by doing, oh, I guess my original problem, it can't be negative. X can't be negative, it can't be 0. Because that wouldn't make any sense at all. X can't be 0, X can't be negative. So yeah, that's why you can leave log X. So, yeah. Because of our original problem, you can leave that off. But you can't leave it off the next one because it could be log, X could be a number less than 1. And the log of a number less than 1 would be negative. And then so you would have to have the absolute values on that part. Yeah, so they are right. Plus C, I got it. Okay, good deal. There's example 7. Now, let's see how they did it. See if they give us any new insight. The solution can be written as an indefinite interval. Oh, isn't that fun? They just said, hey, you can do this. Well, we did it. We wrote it in differential form, then integrated both sides, and that's what we got. Okay? And then your substitution, because the integrand is a quotient whose denominator is raised to the first power, you should try the log rule. Okay. There are 3 basic choices for u. The choice of u equal x, x log x failed to fit the u prime over u form for the log rule. I don't call it a log rule. You just do it, you know. But the third choice does fit. Let u equal log x produces 1 over x over log x, which is just another way of saying du over u. Okay. And that would be log absolute value of u plus c. That would be log absolute value of log x plus c, because u was log x. They never, oh, there it is, yeah. Let u equal log x. Okay, so that's your solution. Y is equal to log of absolute value of log x plus c. All right, now integrals of trigonometric functions. Find that. Anyone want to hazard a guess?
I think you said earlier it was sine squared plus, sine squared x.
Or secant squared x.
I don't know what I'm saying.
Okay, you're thinking secant. Okay. If you took the derivative of tangent x, it would be secant squared x dx. But this is taking the integral of tangent x dx, not the antiderivative. Okay? You're taking the antiderivative, not the derivative. Okay?
You want to change it to sine over cosine?
Ha! That should work. So this would be the integral of sine x over cosine x dx. Now, what would be your next approach? Where would you go with that?
You take a derivative.
We're not taking derivative, taking antiderivative.
That's what I'm going to say.
Huh?
Take an antiderivative.
It's what?
Put u equal to.
Ah, okay, yeah. Okay, now what do you say? Let u equal, you do a substitution, equal what?
Cosine.
Cosine x. Okay, then du is equal to minus sine x. Ooh, I started to write my next term before I got that one written. Okay, sine x dx. Okay, that's what I was. And divide by negative 1. Or multiply by negative 1. I can't write at all, but okay. Or multiply by negative 1. That would work too, but these go away. And now what do we have? Here's your numerator with a minus. the integral of, second,
So I would have negative du over u.
yes, negative, I'll put the negative outside the integral of du over u, which would then be natural log of u, okay, which would then be absolute value of cosine x. What's that? I heard you say something about du over u.
How did you know to put du over u?
Okay. All right. First we chose the most complicated, the innermost part, the most complicated part of the problem, which was the denominator here. Let that be the u. Okay. Then the du was minus sine x dx, so minus du is sine x dx. That's your du with the minus sign on front. What's cosine x? That's your u. So it's du over u. Right? We chose the u to be that cosine x, so that's the denominator, and it turned out that the numerator became your du only with a minus sign out of it. Okay, got it? Okay. And then you plug back in, and here is one place you can do what I've been trying to get you to do, or get them to do. This would be the same as log absolute value cosine x to the minus 1 plus c. And what does that mean?
One over cosine.
Yep. And what's 1 over cosine? Say again? Okay. Yeah. Oh, wait. I'm sorry. I put my minus signs back in. Okay. What is 1 over cosine?
1 over cosine is
Secant. Okay. And it'd be absolute value secant. U plus C. Okay. But let's go back and plug in. Wait, I'm secant x. Sorry. I already did the plug in. Okay. Log absolute value secant x plus C. Got it. Now, I don't know if they take it that one more step. Do they? No, they leave it minus log cosine. They leave it the previous. They leave it in this form, which is fine. All those are correct answers. But seems like you just avoid a minus sign if you write the other. Okay. Now, let's see how they did it. There we go. Okay. The integral does not seem to fit any formulas on our basic list. Oh, boo-hiss. Okay. So what do? Let's use the trigonometric identity and have sine over cosine exactly like y'all chose to do. And then let the... So they come up with this notation again, that out of the blue for a long time back. That's just basically the derivative with respect to x of cosine x is minus sine x. Why didn't they just say d by dx? I don't know. So let u equal cosine x and write that as, see, they, again, if you like it this way better, since you know that's going to be a minus sign, then put a minus out front and a minus here, and then you have d by dx. Yeah. It does the same thing we did, but if you like it better this way, do it that way, okay? That is minus u prime over u, or du dx, du over u, and that would be minus log of absolute value at u plus c, plug back in minus log of absolute value cosine x plus c, and they just leave it right there. Okay. Now, to me, it's a little neater to pull the minus 1 up top, but they aren't focusing on that log property at all. They've avoided it like the plague. I don't know why, but it's fine. Let's now do example 9. They skip example 9, so let's do example 9. Oh, man. The way I'm feeling right now, if I go to this funeral, I'm going to fall asleep in the funeral. I hope I don't, but goodness, I don't feel very well at all. Here is this one. The integral of secant x dx. Now, this is one that there's no way of doing it except by incorporating a really nasty trick. Okay, you could try that. You could do secant is 1 over cosine, but then your u would be cosine x, and you don't have a sine x in the numerator. So that's not going to get you anywhere. That would be my first guess, okay? And it won't help. Here is the really nasty little trick they do. And who would ever think of doing this? Not me, except I've seen it done enough times I know you have to. You're going to multiply this by tangent x plus secant x over tangent x plus secant x. Now that's the first thing that would pop in your mind to do, isn't it? No, I never would have think of doing that. Okay? Now, what does that give you? As your integral, let's do first secant x tangent x I can't write. I don't know what is wrong with my writing today. It just really is awful. Okay. Okay, secant x tangent x over tangent x plus secant x plus secant squared x over tangent x plus secant x. And that's all times dx. Now, is that the way I want to go?
So is this what they were saying a minute ago about you might have to multiply by the...
I think I don't want to do it that complicated. Let's go back and okay. This is ugly, but it's doable. That. Okay. It's secant x, just multiply this thing. Secant x tangent x plus secant squared x over this. Okay. All right. What does that get for us? Well, what would you, if that was your original problem, what would you do next?
Let u equal tangent x plus secant x?
Yes, that's exactly it. Let u equal tangent x plus secant x. And why in the world would you do that? What's the root of tangent x? Secant squared x. And what's the derivative of secant x? No, what's the derivative of it? That's what secant x is, but what is the derivative of it? Go to the front of your book, if you got it, front inside cover.
I don't have the front for us, start chapter
Oh. No. Did you not get the rest of it? Or
No, it's at home.
it's at home.
Fit in my mind.
Yeah, it won't fit in there. Okay, anyone remember what the derivative of secant x is? What would we like it to be?
Secant x times tangent x.
That's exactly what it is. So that would be plus secant x tangent x. Okay? Dx. Right? And guess what we've got then? Be the integral of du over u. And what would that integrate to be?
Log absolute value of u.
Yep. Plus c. Now you plug in and you get log absolute value of tangent x plus secant x plus c. Okay? They put secant first. It doesn't matter. Secant x plus tangent x. I won't want to say that you'd ever do that too, but that's the only one of your trig functions you would need to do that to, I believe. Okay? It's just a trick that works on this problem. Okay? Yeah. Okay. Now, that leads to this. The integrals of the 6 basic trig functions are then summarized below. We know this one. The integral of sine u du would be minus cosine u du. Remember, it's always backwards from the other. Plus c, of course. And the integral of cosine u du is sine u du. The reason is derivative of sine is cosine. Derivative of cosine is minus sine, so you have to have a minus with that. Derivative of tangent is minus the log of the absolute value of cosine u. My word, they have an extra absolute value sign in there, don't they? Yeah, they don't in the book, so they just did. The guy on the graphics end just got carried away here. That's unnecessary. What's that?
I was saying, why is that absolute value line look larger than the other ones?
I don't know. I guess he was trying to distinguish them, but he didn't put one in front. So that's not there. Okay. And then and I would have written this as log of absolute value secant u, and that would have been just to get plus c. And then this would be cotangent u would be without the minus sign, just log of sine, and that's because just write tangent as cosine over sine, and then it works out perfectly, plus c. So this would be what we just saw, log of absolute value secant u plus tangent u plus c. And then the next one would be a minus log of cosecant u plus cotangent u, absolute value plus c. All right. The things, I don't know if these are worth noting or not, and the ice is so dry. These are all opposite signs from each other. The same form, just opposite signs. Minus cosine u sine u. Minus log absolute value cosine u, positive log sine absolute value. Log absolute value secant u plus tangent u minus log of absolute value cosecant u plus tangent. Okay. I don't memorize those. I just look them up if I need them. These two I know, and the other two, most of them I'm pretty familiar with, but I always look them up to make sure I haven't gotten a sign wrong or something, SIGN sign wrong, or SIN sign wrong either, whatever. Okay. So, can we make these even worse? Oh, obviously not. They're going to skip example 10 and 11. So let's us do 10 and 11.
Seems like they always do the easy ones, and then they don't.
Have you noticed that too? Seems like they put that in the slide set, but they don't. All right, these are definite integrals now, so you do them similarly, except you don't have to do the plus c's, and you just put in the limit. Limit from 0 to pi fourth. Oh. The square root of 1 plus tangent squared x dx. What would you do on a problem like that? Okay, you want to do a substitution? And what would you substitute? That u equal
1 plus
tangent squared x. Okay. Then your du would be a 2 tangent x times the root of tangent x, which is
You're saying 2 tangent x?
say again?
You're saying 2 tangent x, so that exponent, the x squared is being applied to the 1, 2. When you take the antiderivative.
Let me see if I follow what you're saying. You tell me if this is what you said now. U equal 1 plus tangent squared x. Is that what you said?
Yes.
Okay, then the next step is always du is equal to the derivative of 1 is 0. This would be 2 tangent x times the derivative of tangent x.
Okay, now I see what you're saying. Because at first I was confused on it almost seemed like you was applying the exponent to we was taking the derivative of tangent x, no, tangent squared and applying that 2 to the
Yeah.
for some reason. I wasn't sure
Okay.
about that. I was
So
like,
are you saying let's scrap this idea?
wait, that one's good. What I thought you was doing earlier was
Oh, okay, well, I'm not finished. Then the derivative of tangent would be secant squared x. And then you have a dx. Is that how you wanted to go on it?
not sure yet.
I don't think so, because now you've introduced a tangent and a secant squared, and there's nowhere you can fiddle with that.
Can't really divide out the
What's that?
I said right. There's no way you can really divide up the 2x and secant squared.
You're mixing your x's with your u's then, and you try to keep those pretty separate. Numbers you can pull out, but not the functions with the variables in it. So I would say let's not do this. There's actually an easier way to go. Okay? And that's recognizing something at the very beginning. And this should have reached out and slapped you in the face. Okay? Anyone know what I'm talking about?
Secant squared.
Yes! Pythagorean identity. 1 plus tangent squared is secant squared. Right? So this would be the integral from 0 to pi fourth of the square root of secant squared. Right? But what's the square root of secant squared x?
Secant x.
It's secant x. And we just did that, didn't we? Wasn't example 9 that? Yes, and what is it? Log of absolute value
Secant
secant x
plus tangent.
plus tangent x. Okay? And we don't need a plus c because we got the limits of integration going from 0 to pi fourths. Okay? Now, time out. Is that okay to do? I would say it's very okay to do because tangent is defined from 0 to pi fourths, and it's always positive from 0 to pi fourths, right? It's going from 0 to 1. The tangent of pi fourths is 1. So going from 0 to 1, perfectly fine to do that. In fact, my inclination is to lose your absolute value signs, and you really do. Okay? But we'll see that. That's the log of. Does anyone know what secant of pi fourths is? Okay. Well, what is secant related to? Yes, it's 1 over cosine. So secant x is 1 over cosine x. And what is cosine of pi fourths? Square root of 2 over 2. Or another way you could write that is 1 over root 2. Right? The only reason I say square root of 2 over 2 is because we rationalize the denominator. When you do this, that becomes 1 over root 2 is just simply root 2. Invert and multiply your bottom one, right? So that would be root 2. I'm going to lose the absolute value bars because that's root 2 plus, and what's tangent of pi fourths? I think I just told you a short time ago. Okay, tangent is sine over cosine, right? And what is sine of pi fourths? Root 2 over 2 is 1. Yes, okay. Now, minus the log of what's secant of 0? Okay. What is secant? 1 over cosine. And what's cosine of 0? 1. And 1 over 1 is 1. Minus, okay. And what's tangent of 0? Someone say it? 0 over 1, which is 0. Okay. All right. I think we got that nailed pretty well. So this is log of root 2 plus 1. I can't do anything to simplify that. And then minus the log of 1. What is the log of 1? 0. So there's your answer right there. Now, yeah, that's about all you can do. You can approximate that as, and I just can't believe they wrote down minus log 1. It's 0, okay. But the log, you just have to plug in what square root of 2 is, plus 1, take a log of that. And they say you get 0.881, which I'm pretty sure is true. Okay? If you got your calculator, check it out. Root 2 is 1.414, plus 1 would be 2.414. Log of 2.414 is that. Log of 2.414. That's ln log 2, right? Okay. 0.881, yeah, that's it. Exactly. All right, let's do, do we have time? Wait, okay, yeah. Yeah, wait. Oh, we went over, didn't we? Oh, no extra charge, though. Okay, you're fine. You don't have, okay. All right, we'll pick up next time with example 11. Okay? Let me get, what's that? I still can't hear it. Say again.
It was just one side of perfect attendance.
One side?
One shy of perfect attendance.
Oh, yeah, one shy of perfect. Yeah, you're absolutely right. I feel bad about that. But,
I think our one that missed on the feel bad about it.
what's that again?
I'm just saying, I think our one that missed on the feel bad about it.
No.
No, that's.
Yeah, that's true. All right. Hey, I was going to give you homework assignments. Yeah, well, leaving too soon. I'm trying to mark my place. Okay, homework exercise. We just that one example left to go. So any of the odds 5 through 27, they're all at calcchat.com. 9's at CalcView. 29 or 31, they're both at CalcChat. 29's at CalcView. Any of the odds 33 to 41, they're all at CalcChat. 33's at CalcView. 43 or 45, they're both at CalcChat. Do 47, it's at CalcChat. That's a little bit more involved problem there. Slope field, we didn't do any of those, but I think you can figure them out. That's 49. If you're not, you can bring them up in class, but we're not going to really do much with those yet. 51 through 57, all those are at CalcChat. 55 is at CalcView. 59 is at CalcChat. 61 and 63 are at CalcChat. 65 or 67, both at CalcChat. 67 is at CalcView. 69 or 71, they're both at CalcChat. 69 is at CalcView. 73 or 75, they're both at CalcChat. 73 is at CalcView. 77 is at CalcChat. There's an exploring concepts here. You can try 79. It should be at CalcChat. And then there's a few others you can take a look at. 81 and or 83 and or 85. 85 is approved. Then using properties of logarithms and trigonometric identities, that's the ones I was trying to get you to do. 87 and or 89. They should be both at CalcChat. Population growth is a CalcChat. 91. 93 is a heat transfer problem. It's a CalcChat. 95 area and slope, that's a CalcChat. You can do any of those you want. You don't have to do them. True or false, 97 and or 99. Okay. They should be at CalcChat. And we'll finish that next time and do 5.3. Oh, we may not do that much on 5.3. I don't think we'll do anything in 5.3. We will go to 5.4 though. Okay. So we may skip 5.3 and go on to 5.4.
How much further are we going to go before we have a test?
In chapter 5?
Yes, sir.
I think this is it. I think 5.4 is going to be it. Let me see. We may do a little in 5.5 because there are some things you'll run into. Actually, there's quite a bit in 5.5 you'll run into. It was 5.6 I was thinking that we... No, we need a little bit of 5.6 too. Goodness gracious, this is one long chapter. We may not do it all. In fact, I don't think we will do it all. But the inverse trigonometric functions, I'm not going to do those. You can look at those. I may just do the slideshow and that's all. Goodness, this is one long chapter. Goodness gracious. Not going to do 5.9. That's hyperbolic functions for sure. That's the one I thought. I kept thinking that's going to show up next. I'll say we're not going to do that. And that's it. Okay. So we'll do a few more. But I'm not going to do all of it. But anyway, sorry about that.